David, do you mind if we wait 2 more minutes? Okay. Mark will join us. Okay, I think we can start. People will still be joining us. And let me just do a short introduction, and David will start. So, just a message. Hello everyone. Welcome to another talk in our webinar series. Today we have the pleasure of having Dr. David Trilling from the Northern Arizona University joining us. He's a professor at the Department of Physics and Astronomy and co-chair in the LSST Solar System Science Collaboration. With his research focused on solar system science, the origin and evolution of stellar and planetary systems, and planets. Today, he is talking to us about the LSST broker SNAPS, the Solar System Notification Processing System. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. David, thank you very much for being with us today, and the floor is yours.
Okay, thank you. Let me share my screen. It says if I do that, it will stop your sound share. Okay, cool.
Okay, sorry.
All right, no problem.
There you go.
Although I'm happy to listen to music for the next hour also, that's fine too. Okay, you see my screen?
Yes, and full screen. Okay.
Okay, perfect. All right, thank you. Well, it's great to be here and also to be there at the same time. Thank you for the invitation and the opportunity to talk to you today. As Rodrigo said, my name is David Trilling from Northern Arizona University in Flagstaff, Arizona, United States. The snow has just started in the last 10 minutes, coming down behind me. So it's fun to be in Brazil and also here in a snowstorm at the same time. Today I'm going to talk about SNAPS, the Solar System Notification Alert Processing System. And before I go too far, I want to acknowledge my close collaborators on this project, Mike Gowanlock, who's a professor here in our computer science department, and Daniel Kramer, who's a really excellent student of ours, who was an undergraduate student and now a master's student working across astronomy and computer science together. Okay, can you see my mouse moving around?
Yes, we can see it.
Okay, perfect. So I'll use that as a pointer during my talk. Thank you. Okay, so I hope I'm going to be able to convince you today that we can answer big science questions with big data. And so these are questions about the formation of the solar system and the origin of life on Earth, really big, important questions. And I think, and I hope that I can convince you that we can address these questions using telescopes, using data from those telescopes, and using smart computational algorithmic approaches to understand these issues about the formation of our solar system. So all of these pictures I'll come back to during this talk and explain what we're looking at here. So first, let me just tell you outline of this talk. I'm going to start with these big science questions. Then I'm going to talk about LSST and ZTF, and I will explain what all of these names mean as we go along. I'll talk about SNAPS and results from SNAPS, LSST expected results, and then at the end, briefly, timeline and conclusions. Okay, so let's start with these big science questions that I mentioned. One of the two questions that I want to focus on here are, how did the solar system form, and how did life on Earth originate? So this picture in the upper right-hand corner, well, I'll come to these pictures in a moment. This picture here is maybe a schematic of how the solar system may have formed. In the lower right, this is an actual image of a comet. And this, of course, is an image of a DNA molecule. And so I'll talk about each of those just briefly. So the first question, how did our solar system form? And again, this picture in the lower right is an artist's idea of maybe what it looked like when our planetary system was forming, a star, a planet, some asteroids, some dust, and so on. And another way to ask that question is, what is the geophysical and cosmochemical history of the solar system? And related to that is the question of how similar is our solar system to other planetary systems? Okay, and the other big science question that I identified is, where did the water on Earth come from? And this, of course, is related to the origin of life on Earth. We need water to have life. And there's an outstanding question in our field about, where did the water on Earth come from? Did it come from, was it part of the Earth as it formed? Did it come from outside, maybe from comets or asteroids? And how much came from different sources? So of course, here's a picture of the Earth, and I put Brazil front and center here. And there's a lot of water, of course. And this picture in the upper right is a picture from Comet 67P from the Rosetta mission. And this image in the lower right, I'll come back to this in a minute, is data from one of the telescopes here on Earth. Okay, so we have these big science questions that are fundamental to understanding how our solar system formed. The question is, how do we probe things that happened 4.5 billion years ago? And here's a key point that I wanted to make. The small bodies of our solar system, so asteroids or comets or similar, are generally unchanged since the formation of the solar system and record key information. So if we study those small bodies, it is a way for us to study things that happened 4.5 billion years ago. Okay, so the small bodies, asteroids, and so on, can tell us a number of things. They can tell us about dynamics, so the movement of material in the solar system. They can tell us about the geophysics of planetesimal formation through the internal properties of those bodies. We can learn about compositions and the chemistry in the early solar system by studying the compositions of those bodies. We can learn about the origin of life In this case, what I want to talk about is focusing on the source of the water on Earth, and so on. And so studying the properties of these small bodies in various ways gives us clues to answering those big questions that I outlined. Okay, so one last piece of this, which is that individual observations of small bodies can be very interesting. So again, here's Comet 67P. And if you've never seen the movies, you should go and find these. There's movies from the Rosetta spacecraft of watching this comet. And so here's the nucleus of this comet, and there's this jet coming off, and actually a number of jets in this image. And the jets change on sort of 10-minute timescales. And you can watch these movies of jets coming and going. And the surface of the comet is reconfigured every few days. It's incredibly dynamic, super interesting. But that's only one object. And how do we generalize from one object to all of the solar system? So this is a map of the solar system. Looking down on the solar system, and the sun is this yellow star right in the middle. And this is not a cartoon, but really a map of every known object in our solar system at the time this map was made, about 750,000 objects. How many of those objects look like this comet on the right? We don't know. And so how do you generalize from individual studies to a whole population, which then tells you about the formation of the solar system? Okay, so what we need is a very large uniform sample of small body measurements. And that allows us to understand the overall properties of solar system small bodies. It allows us to identify what I've called edge cases, or extreme bodies that define the boundaries of how our solar system formed, and also to find rare objects that provide insight into unusual and important aspects of the history of the formation of our solar system. So in conclusion, I hope I've convinced you that we need a large and uniform survey of small bodies in the solar system to answer these big science questions. And there's good news, which is that somebody is building one of those for us. And so this is the LSST, which I'm going to talk about now on the next slide. On the right side is an image, obviously a nighttime image, and the daytime, and the left side here is an inside the dome image from a little while ago. I'll show you some current pictures in a moment. Okay, so here we are at LSST, and I think many of you know a lot about LSST, but let me just give some background so everybody has the same information. So the US National Science Foundation and the Department of Energy together are building the Vera C. Rubin Observatory on Cerro Pachon in Chile. And so I'll show you pictures in a moment. The project will carry out the Legacy Survey of Space and Time, and that's LSST. And I'll use LSST a lot during this talk. And the LSST project, this is important, is not just the telescope and the hardware, but also software and the data stream. And that's going to be the most important part for us, is this data stream. Okay, so here are some pictures. I took this from the LSST photo gallery 2 days ago, maybe. And so this is what the summit looks like right now. And the top image here, this is looking at the outside of the building. And obviously at the very top here is the telescope dome and a multi-story building. There's a lot of technical support as well as computer infrastructure, hardware infrastructure, and so on in this building. To give you a sense of the size, here's 2 trucks parked at the bottom. Here's a door. Here's the porta potty right here. So you can tell this is a very large building. In the top right image, again, it's the same structure now seen as the drone footage from onto the other side. You can see the cranes working to construct the building. Here's way in the corner, here's Gemini South, and here's SOAR sitting at the edge of the ridge. Here on the right side, this of course is LSST at night with an amazing photograph of the galactic center here. That's pretty neat. In the bottom, in the middle here, this is now a photograph inside the telescope dome. Maybe it's not in the dome, it's in the workroom. Actually, I'm not sure where this is. And so here's some people. And this is such a funny picture to me. These look like little Lego people working in this room. I don't know if anybody else sees it that way. So you can see the scale. This thing over here is not the, I think it's not the actual primary mirror, but a dummy for the mirror, so the same size and mass. And here's the secondary mirror in the back. And this is the camera. And over here on the bottom left is yet another image. Here's the camera itself. And here's our Lego people, again, showing you the scale. This camera is really enormous. And the whole project is just a gigantic piece of hardware. Okay, so here's a few facts about LSST. There is a 10-year nominal survey. The telescope itself is 8.4 meters diameter. That's the primary mirror. The survey is carried out where each patch of sky is visited twice in a night and every few nights over the observing season. There are 30-second exposures at each patch, and the depth in each exposure is about 24.5. That's 5 sigma, depends a little bit which band we're talking about. The camera has a 9.6 square degree field of view, 3.2 billion pixels. The nightly data volume is 20 terabytes, and the 10-year data volume is 60 petabytes. It's a lot of zeros. Okay, so if you wanted to look at an image, okay, here's your MacBook Pro, and okay, I've got 3.2 billion pixels. I have a MacBook Pro. How does it work? Well, you actually need 542 laptops arranged in an array to look at a single LSST image. And then you need to redisplay every 30 seconds all night long for 10 years. Okay, so the conclusion is that no one will ever look at a whole LSST image. It's not possible to look at an LSST image. And in fact, the data volume is so huge that the data must be analyzed algorithmically with computers. Nobody's going to look at images and say, oh, here's an interesting thing I found. We first have to do an algorithmic study. So the bottom line is that we need to build the software tools to analyze the LSST data in order to answer those big questions that I mentioned before. This is a big job. It's a lot of data, and we need computational sophistication. So there's good news, and this is the last part of this introduction, which is that we can practice with ZTF. So ZTF is the Zwicky Transient Facility as a survey being carried out with a 1.2 meter telescope on Mount Palomar. And here in the upper right is a picture of that observatory. And they are carrying out an LSST-like, that's in quotes, public survey since 2018. So now three and a half years or something. And LSST-like means that they are observing a large area of the sky. They have a cadence that's like LSSTs. The data products are like LSSTs. And so we can use the ZTF data as a test bed for LSST software development. Okay, so I'm going to put all this together. We have big science questions that require big data to answer. We have surveys that are producing a large and uniform data set, and we have a need for advanced computational approaches. The conclusion is that we need SNAPS. Okay, that's what I'm here to talk about. So SNAPS is the Solar System Notification Alert Processing System. SNAPS is an official LSST broker, which means we have direct access to the alert stream coming out of the observatory. And a lot of the results I'm about to show you in the next 20 minutes or so come from SNAPS paper 1. We've had paper 0 and paper 0.1, and now we're doing the real SNAPS paper, which has a lot of architecture and database and so on results. Okay, let me check my time here. Good. So I know it's not always that much fun to look at an architecture diagram in a talk like this, but I think it's important. I want to talk to you about the parts of SNAPS, and then I'll show you examples from each of these aspects. So I'm going to walk through this. I have the blue box to highlight both the text on the left and also the flow chart on the right. So ZTF and also LSST issue alerts for transient objects. So ZTF is doing this now. Every night we ingest these alerts. LSST will do so when it starts in a couple of years. Okay, so the alerts are issued by the surveys, and a transient object in this case means something, some piece of sky that looks different than the historical observations of that piece of sky. So you might have a supernova that, that RA index got bright all of a sudden. That's transient. You could have a variable star, or you could have a moving object where you might have a blank piece of sky, and then an asteroid moves into that piece of sky and then moves out. And so that's identified as a transient object. So the surveys can identify, in this case, they can say, oh, we know which asteroid that is. We issue an alert and we tell you the asteroid name. We tell you RA, DEC, magnitude, time, filter, some other stuff, some metadata, and that's part of the alert package. Okay, so what do is we ingest those alerts. And there's two ways to do this, and I'm showing them here in the top right. One is we can listen directly to the survey. At the moment, the way we work is we're listening not directly to a survey, but through a different path. So there's another broker called Antares, which is listening to all the alerts. Antares listens and they rebroadcast an alert stream that is only solar system objects. So we're listening to that, oops, sorry. That is this, this pathway here. So we're listening to the solar system object alert stream. We ingest the data, which again is the observations and the metadata. We also are ingesting adjacent databases like Sloan, NEOWISE, 2MASS, the Minor Planet Center, and others. And we are able to attach information from those adjacent databases to object records in our database. And I'll show you an example of that later. Okay, so we have, as I said, a database of observational records. For a given asteroid, I know every time it's been observed by ZTF and all of the magnitudes and so on. And we also are creating a database of derived properties. So from this time series photometry, we can derive properties of asteroids. And I'll show you that also in this talk. Okay, now we look for objects of interest. And we do that in two different ways. Shown here on the right side is what I've called the real-time or nighttime processing, and that's in the red here. And this is looking for an example where an asteroid appears different than we expected. So we have a historical record for this asteroid, and we have an expectation that it might have a given magnitude plus or minus. And maybe it's a lot brighter than that magnitude. That's unusual. Or maybe its color is different from all of the historical measurements of its color. That's unusual. And so that's called a self-comparison, an object that is different from itself in the past observations. That's during the night we do this. And then during the day, we have what we call an ensemble comparison. So this asteroid has properties that are not changing with time, but those properties make it different from all of the other asteroids that we have in our database. That's also an unusual asteroid, and we identify those as well. We do that during the daytime because we don't need to do this real-time processing for that object. So that's also a path to look for objects of interest. That's in the blue here. And then we publish alerts in a database. So in each of these cases, we can say, aha, we found something interesting, and that's an alert that we can issue. And we also have a database and a web portal, and I'll come back to that at the very end. And finally, there is the opportunity for us and others, of course, to do telescopic follow-up of objects of interest. And I'll show you that at the end as well. Okay, so that's our flowchart of snaps. Let me give you some, oh my gosh, I have an XXX here. That's so embarrassing in my talk, I apologize. So since 2018, we've been ingesting these observations, and we have about 10 million moving object observations ingested, and that's about 400,000 unique asteroids. And what I'm supposed to remember to change here on my slide, and I'll just tell you, is that what I'm going to show you here in the rest of this talk is what we call a snapshot. That's a nice name because it has the word snaps in it. This is our highest quality data from the first about 2 years of the ZTF data alert stream. And so these are objects that have more than 50 observations each and various high quality data cuts that we've made. And that's what I'm going to show you the results over the next 10 or so slides. Okay, so let me show you a few things about the database, about our asteroids, our current results. This is a snapshot of the database of this high quality snapshot. This is a histogram of number of observations. This funny pattern with the gaps in it is just because of the auto binning from Python. There's no reason, no physical reason for that. Okay, so this is the number of observations. So asteroids with a given number of observations. So here's 100 observations. We have about 500 asteroids with 100 observations. We have about 2,500 asteroids with 50 observations. And you can't really see it, but this plot goes all the way out almost to 300. So we do have asteroids that have 300 or so observations historically over the few years that we have captured in this high quality snapshot. I want to show you briefly some of our derived properties. So two main things that we derive are the color of an asteroid. So ZTF observes primarily in the G and R filters, and so we derive a G minus R color. And we also derive a light curve period and amplitude. And so the idea here is that an asteroid is not round or not spherical, but more sort of potato shaped or oblong or elongated. And as that body rotates around, the apparent magnitude gets brighter and fainter and brighter and fainter. And from that time series photometry, we can extract the period and the amplitude of that body. Okay, so here's a couple of examples. This is a histogram, again, of color that we've derived for this high quality snapshot. Here's the derived color, and this is just number. The blue here is showing the high quality data, and then the purple is showing the highest quality. So we have a subset within the high quality data set. And you can see this highly bimodal distribution. There's a peak here at about 0.47 and another peak at 0.67, some numbers like that. And it turns out that this is well known and not a surprise. The asteroids in our asteroid belt generally fall into two taxonomic or compositional classes. One is called C-type and one is called S-type. And the C-type is well known to have a color of about 0.47. And the S-type is well known to have a color of about 0.67. So there's no surprise here, but it's a nice confirmation that we got the result that we expected. Here's two more histograms. On the left, I have light curve amplitude. So again, this is the max minus min, essentially, of the brightness variations. And you can see we have a peak at about, I don't know, 0.15 or something like that, and this very smooth distribution out to magnitudes, amplitudes greater than 1 magnitude up to about almost 1.4. There's this gap here at the very bottom. We're not sensitive to objects there because the photometric uncertainty from ZTF is typically about 0.1 magnitude, maybe a little better. So an amplitude that's the same size as the error bar or the uncertainty is not, you can't extract that from the data. So probably this distribution keeps going up, but we don't have any results there. We can't tell you. So that's amplitude on the left side. And on the right side here is light curve period. And this is logarithmic of period, log of period. So this is 10 hours, here's 100 hours, here's 1,000 hours. And you can see we have, again, a reasonably smooth distribution, not quite as smooth, but still pretty smooth. And these very short periods, we're not querying those in our data, but I'll show you an example later on that is down here. The main thing you notice, of course, is these giant spikes, one here and one here. These are aliases. This is 24 hours and this is 48 hours. So ZTF, of course, is a telescope on the ground, on the Earth. We have night and we have day, and then again, we have night and we have day. And so every time series data of any kind for any astronomical observation has an alias and a very strong periodic signal at 24 hours, simply because of the rotation of the Earth. And so, you know, many of these solutions are not the correct solution. We're being confused by an alias. We've been developing techniques to remove those aliases, and I think we know how to do it, but I'm not showing those results yet. So don't be confused. There's not really this many asteroids with 24-hour periods, but there are probably this many asteroids, you know, because you can interpolate this curve and see what the distribution should be. Okay, let me now also talk about our derived properties. Those were all histograms. I want to make some plots here of different properties against each other. So this is semi-major axis on the bottom, which is distance from the sun. So the sun is at 0, Earth is at 1, and the main asteroid belt is between about 2 and 3.5 AU. And now I've got, again, that G minus R color on the vertical axis here. And S-types, again, are about here, and C-types are about here. And you may be able to see that it's hard to tell in this plot, but there's a density of objects here, S-types in the inner belt, and a density of objects here, C-types in the outer belt. And this, again, has been known for decades. that the distribution of compositions in the solar system changes as a function of distance from the sun. But we have a really, really high quality data set that shows this, larger than any other data set has ever been to show this. And what we've made here is a compositional map in the solar system. And think back to those big science questions. This is going to help us address the question of how did our solar system form by making this compositional map throughout the solar system. Okay, here's another similar plot. This is now color on the bottom. I've swapped it. And here's NEOI's albedo. So albedo is the reflectivity of an asteroid. And again, we know very well from various other studies, previous studies, that C types should be here and S types should be here. C types have low, blue color and low albedo. S types have a red color and a high albedo. And we see that very clearly, a big clump of objects in both cases. So again, haven't learned something new here, but it's nice to confirm this map with a very high fidelity sample of tens of thousands of asteroids. And finally, now I've got period versus amplitude. So I showed you the histograms of those two. Now I've plotted them against each other. Here's period on the bottom, again, logarithm. And here's amplitude and magnitudes. And so 1 magnitude is here. It's kind of the biggest that we have. And here's 0.1 magnitudes. And of course, below that, we don't really have any signatures that we trust. Here's our two aliases again at 24 and 48 hours. And you can see that most of the asteroids are here. Relatively short periods and sort of moderate amplitudes. But we do have asteroids all the way out here, and I'm going to show you an example of that. So again, here's, this is log scale, so this 3 is 1,000 hours, and this 4 is 10,000 hours. And you see we have distribution of asteroids. We stop at 5,000, but we have asteroids all the way out there. So I'll show you an example of that in just a moment. Okay. So that's some snapshots out of our database. I want to tell you about 2 validation techniques that we do in our database. One is to compare our results to results from known databases. So here's an example. Here's our SNAPS period on the y-axis. And on the x-axis is asteroid periods from a different database, which is called the Light Curve Database, LCDB. Don't worry about the details. But of course, for solutions that are the same in 2 databases, we should be along this 1-to-1 line. And you can see that we are largely along the 1-to-1 line. There's a 2-to-1 alias here. Here we've got our 24 and 48 hour aliases and some other structure in this figure, which is complicated to understand. But overall, our match is quite good. Excuse me. Here's another comparison. I keep switching the axes. I apologize. This is the SNAPS G-R color here on the y-axis, and here's the Sloan SDSS G-R color on the x-axis. And again, the 1-to-1 correspondence is right through the middle of this cloud. The match is quite good. The RMS, or the residual, is a like 1-point-something% difference between these two on average. So that is nice confirmation that our color measurements are good. And finally, this is a figure showing 2 different properties. This is the H here is the solar system absolute magnitude. Don't worry about what the definition is, but we have values from SNAPS, and this is an external catalog from the Minor Planet Center, and we compare. And again, 1-to-1 slope, the match is quite good. Here for SNAPS, we derive an H both for the G band, that's in green, and the R band in red, because we have 2 filters from ZTF. And so this offset between the 2 is actually measuring the mean color of asteroids, the G-R color. Okay, and our final validation step, in addition to those external catalogs, we also have synthetic objects, a synthetic object population that we've built, and we push that through our processing as well. So we take 10,000 asteroids, we randomly assign properties for a light curve, which is just a sine curve, really, with an amplitude and a period. We assign photometric uncertainties, and we sample at a ZTF-like cadence, and then we look for the solutions, and we compare the solutions to the input properties. So here is number of observations for synthetic asteroids. So this is 100 and this is 1,000 observations. And this ratio here is the ratio of the period we derive to the period that we assigned. And so a ratio of 1 means we got the right answer. You can see almost all our solutions are on this line. We have some scatter here where we have a smallish number of observations. But when you have a large number of observations, the match is almost perfect. And here's another test of this. This one, yeah, this one's complicated. I'm going to skip this one and make sure I have time to get to the other plots at the end. I'm just going to say that our color solutions are also pretty accurate. Okay, so I really want to make sure I had time for these interesting objects. So that's where I'm going to go here. These are now individual objects that we've pulled out of our database that are interesting. Okay, the previous plots were all sort of summary plots of the whole population of asteroids. Now let's talk about the individual interesting asteroids that we have found. Okay, so on the right side here, I've shown you this image a couple times. This is a postage stamp for an asteroid that was observed by ZTF. And we went to go look at it because we knew this was an active asteroid ahead of time. There was a lot of chatter on the internet and emails and so on. Oh, this asteroid is active. So we knew to go look at it. Hopefully, I don't know if you can see it very well. The image is not great, but anyway, here's the asteroid itself. And there's a tail that extends off in this direction. I don't know if you can see that with this stretch. But anyway, that's what we're looking at here is a tail. And so an active asteroid is an asteroid that probably has water on or near its surface. And that water, as the asteroid gets a little bit closer to the sun during the path of its orbit, the water vaporizes and it produces this tail. And so it looks like a comet. Okay, we call that an active asteroid. And because this tail is being produced by water, by measuring these, we're inferring the presence of water on these asteroids. Okay, so we happened to go look for this asteroid because we knew it was interesting. But I told you before, we have 10 million ingested observations. Nobody wants to look at 10 million postage stamps of asteroids. So how do we find this algorithmically? So this plot in the middle shows tries to capture that. We have a multi-dimensional parameter space where we know lots of things about our observations. Here I'm showing you just 3 dimensions because it's hard to present more than 3 dimensions in a plot. On this vertical scale is a real bogus score, which tells you sort of how much like a point source your observation is. This one here, mag 18/8, is the ratio of the magnitudes in 2 different aperture sizes. And then this elong is the elongation of the source. Is it round or is it elongated? And it's hard to see in a 3-dimensional plot, but you can probably see that there's a big clump of objects over here. And then there's a very small tail coming out this way. And this orange star is this observation right here. So clearly we've identified a multidimensional space where at least this outlier stands out and says, hey, these are the properties that a measurement might have if it's an active asteroid. Okay, so that one's confirmed and we're able to test it because we knew this one was an object of interest. So now what do? We take those other objects and we go to the telescope. So this is the Lowell Discovery Telescope. It's about an hour drive that way from where I'm sitting. And it's a 4.3 meter telescope and we'll be observing there Saturday night, assuming the snow doesn't stick around too long. And we're gonna try to confirm some of these other data points here. And do they have a tail like this image in the right here? Okay. Last piece of outliers I wanted to share with you is about very fast and very slow rotators. Okay, so these are 2 plots, 2 different asteroids on the left and the right, but the 4 panels are the same. So let me introduce that. This top panel is essentially the magnitude as a function of time. So it's our time series photometry in the G and R band. The second panel is a periodogram. So where is the power in this, the periodic power in this time series? The third panel is now, we take this peak power and these data and we phase them. And so this blue curve is the sine curve with that period. And we phase the observations according to that period. And then the fourth panel is the residual. And that's the same on this side, the same 4 panels. So what I want to show you here on the left side is that we found an object with a period of 924 hours. And on the right side, we found an object with a period of 0.4 hours, which is 20 minutes or something like that. And you can, again, look at this third panel. The phase data looks quite good. I'm quite confident in this solution. And this one over here looks pretty good as well. The amplitude is smaller, and so it looks like the error bars are big. Still is a pretty good solution. And we're going to be confirming this object right here at our telescope on Saturday night as well. Okay, so what's important about this? Well, almost all asteroids, I don't know if you can remember back, but almost all asteroids have rotation periods between a few hours and maybe 50 hours or so. And there's a very small number of asteroids that have periods on either side of that. And so we're finding asteroids, these extreme cases in our database, the very short periods and the very long periods. So we published a paper earlier this year led by Nick Erasmus that we found that about at least 0.4% of asteroids are rotating very slowly, that is more than 1,000 hours. And until we published this paper, the number of asteroids rotating with periods longer than 1,000 hours was 1. We published 40 in that paper, and we've got hundreds in our database. We just published the first 40 just to get the paper out. It also appears that at least that fraction may also be rotating very fast. That is less than a couple hours. And that is work that we're still confirming those results. So I'm not going to put a number on it yet, but I will tell you that in both cases, we can place strong constraints on asteroid internal strength. Okay, because what happens is if an asteroid is rotating very fast or very slowly, if the internal strength is not a certain value or greater, then the asteroid basically either flies apart or condenses and becomes round again. And so you require certain strength to match that rotation period, these extreme rotation periods. Internal strength tells you about internal structure, which tells you about formation of the asteroid and of the solar system. Okay, I think this is my last SNAPS plot, and then we'll do a wrap up. So in the same paper, in Nick Erasmus's paper, we showed some telescopic follow-up. So in this study, as I said, we had 40 asteroids published in that paper. And so what we took the asteroid that we were most confident about its long period and the asteroid we were least confident. In fact, we had reasons to think it did not have a long period, although it showed up in our results. And we observed them with a robotic 1-meter telescope that we have here in Flagstaff. And robotic telescopes are perfect for long period asteroids because you just do it every few weeks and no human has to stay up all night or anything like that. So this is time in days, like 100 days. Here's absolute magnitude for the purple asteroid, and then here's for the orange. And you can see this purple one, the very long rotation period is easily confirmed. And this orange one, we knew within a few days that the long period was not correct because within a night you could see very large variations in the amplitude. And so we knew that the rotation period was going to be something like a few tens of hours or something like that. And it turned out to be about 32 hours. This one turned out to be about 3,700 hours. And if you're trying to do the math in your head, I did it for you this morning, 3,700 hours is 154 days. So this is an asteroid, few kilometers in size, that is rotating so slowly that it takes 154 days for this asteroid to do one complete rotation. Very unusual. Okay, so here's my final thing about SNAPS. I think this is the last one, which is another flow chart, but now I've told you some of the parts so I can give you a little bit more details. We're analyzing data that's coming from ZTF or LSST. Coming in this way, we have an outlier detection scheme where we look for these outliers. We find candidate active asteroids. We find candidate super slow rotators and super fast rotators. That's what those stand for. We issue outgoing alerts to our follow-up telescopes. We also take these candidates and we train and apply our supervised and unsupervised machine learning approaches to improve our outlier detection scheme. And then we go back and we can analyze the data again. And at the end, of course, we have our science results at the bottom. Okay, so I'm not going to talk about this machine learning. That's the subject of a whole other talk, and it's being led by my colleague, Mike Gowanlock in our computer science department. But I do want to highlight that it's part of our processing. Okay, so we've done all that work on ZTF. Now we want to scale for LSST. So ZTF is about 10% of the LSST scale. In the LSST era, we get new data every 30 seconds all night long for 10 years. And we need to do this real-time processing where we search for activity in less than 30 seconds because we get new data every 30 seconds. And we need to do our daytime processing, for example, this rotation rate business, in less than 12 hours. And if we don't meet either of those criteria, then we fall behind and we'll never catch up because there's more data coming and coming and coming. Okay, so one of our computer science approaches has been to implement a GPU periodogram approach. So Lomsgargle periodogram is the, or Lomsgargle approach is usually the technique that we use. And what I'm showing here on this plot is from Mike Gowanlock's paper earlier this year. This is the number of frequencies that we searched in our periodogram. So from 1,000 up to 1,000,000. And here's the time it takes in seconds, as a logarithmic scale. The blue and orange plots are two different CPU architectures, and the black and the red are two different GPU architectures. And you can see a graphics processing unit. Sorry, I didn't say that before. So you can see that out here at the largest number of frequencies, which of course gives you the highest fidelity for your results, we have about a factor of 100 speed up from CPU to GPU. So this actually has made this LSST scale possible, because now we can do all this work on our GPU machines very fast. So here's our SNAPS conclusions, and then I'll give you the whole conclusions for the whole talk. I think I'll be on time here. So SNAPS works on ZTF observations at ZTF scale. We have this new GPU implementation, and the SNAPS database enables a range of science cases. What is the distribution of asteroid strengths? We get that from these rotation periods, and that tells us about the formation of the solar system. And what is the frequency of active asteroids? And then we're going to do this again from those machine learning searches for these activity, these tails on the asteroids. And that tells us about water in the solar system. So our future work for SNAPS is that we're working on a public value-added alert stream. Right now we have an alert stream that's internal only. Value added means not only do we tell you what ZTF reported, but we also add our derived properties and the adjacent properties from our adjacent databases. And we are working on a publicly accessible database and web portal. Again, we have an internal database and web portal, and the publicly accessible part is coming within the next 12 months, so in 2022. And finally, we're going to be testing SNAPS at LSST scale, which is 1,000 asteroids every 30 seconds. Okay, so I think I have three more slides. LSST expected results. When LSST comes online or over its 10-year lifetime, we expect to have about 5 million asteroids observed hundreds of times each. We estimate that that may give us about 10,000 super slow or super fast asteroids, which is a factor of 100 improvement over the current science catalogs. And perhaps hundreds of active asteroids, which again would be 100 times improvement over the current number of known active asteroids. And those increases of a factor of 100 give us maybe 100 times increase on the fidelity of answering our science questions. Okay, so here's the timeline. I'm sorry to show this terrible figure. This is from the LSST project timeline and summary, but it has all the right information on it. But let me just show you, just focus on the top line here, which is calendar year 2017, 18, 19, 20, 21. So here we are today, right here at the very end of 2021. And I've highlighted over here on the right that the LSST project predicts that the earliest they could be ready is August of 2023, and the latest is February of 2024. And of course, it's probably going to be the latest because it'll, you need the extra time and you finish at the very end. So I've put that arrow here. Data is, sometime in the beginning of calendar year 2024. So really that gives us about 2 years from now until then to make sure that we can work at the right scale and that we can extract the information from the LSST alert stream so that on day 1, we are ready to do science with the LSST asteroids. Okay, here's my last slide. So our conclusions, here we go. Some big science questions can only be answered with big data. These are questions about the formation of the solar system and about the origin of water on the Earth and the origin of life on Earth. LSST will provide the data stream that we need to address these questions, and SNAPS will provide the analytical tools that we need to address those questions. So between the two, SNAPS plus the LSST data flow, which will be by 2024 at the latest, we can place new constraints on the history of our solar system and of life on Earth. Thank you very much. I appreciate your coming to this talk. Thank you.
Thank you very much, David, for the very interesting talk. We now have time for questions from the audience. If you joined us on YouTube, please put your questions in the comment section. And if you joined us here on Zoom, please raise your hand and ask your question. So, questions? Go ahead, Julia.
Okay, hi, hi, David.
Hello.
Hello. Just a few questions, a few things I did not understand well. First of all, is why do you need, or why is it useful to ingest alerts data, or I don't remember Antares or alerts data, as you mentioned in the beginning, if you are directly connected to the LSST stream?
Yes. So I have my slides here. Let me put this figure back up and I'll share again so I can point to that, except I can't figure out how to share. Okay, I don't know. I lost my control to share. I'll just talk about it. So we could listen directly to the ZTF LST. Of the alert stream, about 10% is solar system and 90% is not. And so if we listen to all the alert stream, we would take 90% and just throw it away and only keep the 10%. So that's one reason. The other reason is that the LSST project is concerned about too many connections to their alert stream. They have a limited number. I don't know why this is. It seems like this is 2021, we should have infinite connection. But anyway, so they have asked us if we would listen to Antares instead and only listen to the subset rather than to the mainstream. And we said, fine, we don't care because we don't want all those stars and other business anyway.
Okay. Well, the next question is, I have already asked it in another opportunity, not to you, but concerning the new objects, the new discovery of small objects. For instance, suppose that a new object is discovered. Then after some time, it will no longer be a new object, it will be a current object. Is it possible with snaps to trace back the observations of the object previous to the determination of its characteristics or orbits that also gave it an identification that promoted him to a known object?
That is a good question. Okay, so there are many answers to that. On day one of LSST, they turn on the telescope and they find, on night number one, they find 1 million new asteroids that nobody's ever seen before. Okay, good luck. Nobody can deal with that data. But over time, those, as you said, those new asteroids will become known asteroids, and then they enter our database and we have their properties. The way that the identification will work, maybe not on the first day, but later on, is that LSST will observe on night number 1, maybe night number 5, and maybe night number 10, after which time the object is designated and we can enter it into our database. So we've only missed a few observations, those very early ones. Mm-hmm. We have not thought about how to go back and get those observations, but I think we could do it because it's in the observational record that LSST has. We could go and pick up the unique ID or whatever it is for those measurements and bring them in. So I'm going to write that down. We haven't done it, but it's something that we could do.
Okay. My last question is, first of all, congratulations for the extraordinary work. And if you want to join or to use for instance, your value-added data, your value-added results, where can we learn how to join these maps? How to join and how to connect perhaps our softwares to be fed directly by snaps?
Yes. So as I mentioned, at the moment, all of our interfaces are internal, not external. They will be eventually. But before that, I think several of us may be talking, I don't know, next week or sometime soon about just collaboration. And so let's put that in our conversation and talk about what we can do in the meantime.
Okay. Great, thanks a lot.
Yeah, good. Thank you.
Thanks, Julio. More questions? Well, while we wait for other questions, I have several questions actually.
Okay.
First, I don't know if I missed it, but you were showing some results about asteroids from the ZTF. Are you focusing mainly on the main belt, or are these asteroids all over the solar system?
Anything that's an asteroid we ingest, but almost all of them are in the main belt. We have, I don't know what the number of near-Earth asteroids is right now. It is not a very large number because
I think 20,000.
I'm sorry?
I think around 20,000. I had this number.
Yeah, I meant the number in our database, which is very small.
Okay. Oh, sorry.
Yeah. And the reason is because all those results I showed you, we require 50 or more observations before we start to do the periodogram and such.
Yeah.
And the near-Earth objects, not very many have been around enough times that ZTF observes them more than 50 times over the last few years. So we have a few, I think we have a few hundred, but we don't have thousands. Mostly main belt, because we get those every year. We do have, I don't know, 50 or 100 objects in the distant outer solar system at TNOs at 48U. They're the very bright ones, so we haven't learned anything new really, but it's kind of interesting that they show up. And we have hundreds of Trojan asteroids, and I mean, everything is there, but it's mostly in the main belt.
Okay. And I was very surprised with some results in the various low rotations. And I was thinking, because the shape of the phased light curve is very sinusoidal. Do you think that it will be possible that maybe these are detached binary systems that rotate very slow? And another question that I have to myself is, would we be wait a minute. Would it be possible for us to observe like a phasing effect, like the moon phases in a binary system of asteroids?
Well, I don't know for the second one. And even if you could observe it with a dedicated telescope, could we be able to see it in the ZTF data, which, as you know, is sparse and not particularly high accuracy photometry and so on. So I don't know. For the first one, for the binaries, we thought a little about it. We haven't thought very much. And I think somebody who knows more about geophysics than I do should, do the calculation and say, is it more likely to be a single object, or is it energetically more likely to be, as you said, a double or something? I don't know. Yeah, good question.
Yeah, because it's very unusual, very odd to have so slowly rotated.
Yes.
And finally, do you have any strategy to run your periodograms? Because will you do it every night? Because it's a lot of objects.
Yeah, so that's this GPU implementation. And we can do the whole, right now our whole catalog, which I said is 400,000 asteroids, and the high fidelity group is about 65,000 asteroids. The high fidelity group, we do the whole thing in 5 seconds now on our GPU. It's amazing.
Yeah, so it's amazing. It's amazing.
Yeah, and that I can share with you the reference, but the code is all on GitHub and it's ready to go. So
sure.
It would be great actually to have additional users and to test it out and see if it's useful for you.
And well, now my final question: will it be open for those that want to in the future that want to use, or will there be some kind of private access to the SNAPS database to the products that SNAPS will produce?
Yeah, it will be public access.
Okay.
To the whole world. Yeah, and the alerts that we send out also, here's an active asteroid, here's a slow asteroid, those are also public. And so we will eventually the web page will be public facing and there'll be instructions how to connect to the alert. And I don't have a screenshot here, but the current version of the database has, high level description and look at your favorite asteroid and some analysis tools and so on.
Okay.
Yeah.
Oh. Thank you. Thank you very much.
Yeah, good.
Okay. Do we have more questions? Okay, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on the LIneA's YouTube channel. And for the next week's webinar, and also our closing our webinar series this year, we will have joining us Dr. Richard Cron from Fermilab. We talk entitled News from the Dark Energy Survey. Thank you everyone for attending, and a special thanks to David. Thank you very much.
Thank you for the opportunity. I look forward to talking more about all these things.
Okay, thank you. And so do we. Everyone have a great day. Stay safe, and I hope to see you all back next week. Thank you.
Thanks, everyone.